Bismillahirrahmanirrahim. So let's start with the today lecture. In this lecture, I'm going to teach you the one of the application of the quantum mechanics, and that is the calculation of the absorption wavelengths by using the translation movement of the particle in one-dimensional box. And you can also say this is the electronic absorption spectra of the organic molecules. So particularly it will be for the polyenes, and polyenes are having the multiple single and the double bonds, and they should be in an alternate single and the double bond. And one of the example is the this beta carotene, and this is the structure of the beta carotene. So let's start with the calculation, how you are going to calculate the absorption wavelength, that means at which this is going to absorb the light, which may be the UV visible or the IR or maybe any other electromagnetic radiation. So here, what is the important over here is this is the skeleton structure. That means this beta carotene is having the alternate double and the single bonds. Let's count how many are there, the double and the single bonds. So this is the, let's suppose this is the carbon 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So there are alternate uh, 22 carbon atoms where this is having the single and the double bonds. Now, how many single bonds are there and how many double bonds are there? So these are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 are the double bonds, and the single bonds are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are the single bonds. So it is written over here. So I have just explained how to calculate the double and the single bonds and the total carbon atoms, because these are the important to calculate the absorption wavelength. So there are 22 carbon atoms in this alternate single and double bonds, and there are 10 single bonds and the 11 double bonds. And now the next important is the what is the length of the box. And here we are considering this molecule as the total length starting from here to here. This is the length of this molecular box, and the length is 2.94 nanometer, and you can calculate by using the total number of the single and the double bonds. Here this is the average bond length is taking for the carbon carbon is 140 picometer, and this is written over here. So average bond length is 140 picometer, and there are the 21 carbon atoms. So sorry, 22 carbon atoms. So this is mistakenly written over here. You may correct. Let's correct this one. I'm also verifying if it is the correct. So 140 multiplied by 22, that would be equal to 308. So you may later correct this calculation, but I am going to teach you the way how to calculate this one. So there are 22 carbon atoms, and please again recalculate the whatever it is the length of this box or the molecular box. So simply the average is 140, and you are multiplying with the number of carbon atoms. You will get the value of the the total value that would be 2940, and or you can convert the picometer to the nanometer 2.94, or you may convert into the meter, which would be 2.94 exponent minus 9. So this is the length of the box. Now what another important thing is, now where is the transition of the electrons from which energy level to another energy level. So there are the 11 double bonds, so they may be like energy level 1 2 3 4 and up to the 11. So transition would be from a number of 11th energy level to the 12th energy level, and the energy level in a similar way, these are displayed over here, energy level 1 2 3 5, and similarly you will come up to the energy level 11, because there are the 11 double bonds are there, and the transition would be from 11 to 12. So this we have actually did the some of the basic information over here. So now moving to the further calculation, I have displayed over here what would be the length of the box, or the length of this molecule beta carotene, and in a similar way you can calculate another molecule which is 2.94 over here. Starting from here to here, this is the length of the box. So actually this conjugated pi system extend over the 21 bonds, 22 carbon atoms. So I think I'm going to move further. So because there are the from here to here, there are the 22 carbon atoms, but the double bond is starting from here to here. So there, if you calculate the extension of the double bond, that would be the 21 carbon atoms. So it was written right in the previous slides. So let's see again. So this is the 2.94 is the length of this molecule. Now, how can you calculate the energy difference and the wavelength? Because our objective is to calculate the wavelength of the absorption wavelength of this polyenes molecule. This is the equation which we have already derived in the previous lecture, and it is the link is given over here. You can also watch again. Now I am using this one because this n is important, and n we have decided because there are 11th double bond, so there would be the transition of the electron from energy level 11 to energy level 12. So the value of n would be the 11. So the n is important because this you have to decide, otherwise all other parameters are constant, and n and L is the variable. It depends on the molecules, and this n we have calculated, it is energy level 11th, and L we have also calculated, that is the length of the molecule, which was the 2.94 exponent minus 9 meter square. So you have to put the values over here. This is the 2 is the constant, 11th is the nth energy level, plus 1. This is the Planck constant. You have to take the square. 8 m is the mass of the electron, because this is the electronic transitions, and this is the length of the box, as we have already calculated. When you solve this one, you will get the energy of 1.60 exponent minus 19 joule. So further, it is very simple. You can calculate the first the frequency by using the Planck's equation, or the Bohr frequency radiation. That would be the E is equal to h mu, and mu will be equal to c over lambda. You may calculate directly, or you may calculate step by step. So first I am going to use this equation to calculate the frequency, and this frequency would be delta E over h, and delta E value is given over here, H is the Planck constant. When you put the value, you would get the answer to 0.41 exponent 14 per second. So this is the frequency of the particle. So then you would put the value of the frequency over in this equation, because mu will be equal to c over lambda, or lambda would be equal to c over mu. C is the velocity of light, 3 exponent 8 meter per second, and this is the frequency you have already calculated, and that would be equal to 1.244 exponent minus 6 meter, and you may convert into the nanometer as well. So this is the way you can calculate the wavelength uh, of the polyenes molecule, and this is actually the absorption spectra of the polyenes molecule, which you would get from the UV visible spectroscopy or the IR or the other spectroscopic technique. So actually, this is the quantum mechanical approach to calculate the absorption wavelength, and this is the actually the experimental value of this beta carotene is given over here, which is the 4.97, and this is in the visible range of the electromagnetic spectrum. So this is one way it is given in one of the book, and I am going to show you another calculation which is more appropriate and more uh, uh, it is more desirable, or more in a sense which is going to give you accurate value near to the experiment value by using this way of the calculation. So there is little bit different, and what is different actually, in the previous example we have taken the average bond length of carbon-carbon double bond, and another way is to calculate each of the bond length of the carbon-carbon double bond and the single bond, and you have to consider also the what would be the terminal atoms as well, what would be the radius of the terminal atom. So this is I am going to show you over here. And now again do the same thing as we have done before. What would be the nth energy level? So there are two double bond and one single bond, and this is given over here, the transition of the electrons. You have to fill up first energy level this, and then this is the second energy level, because there are the two pi bonds are there, so two electrons are here, two electrons are here. So transition would be from energy level 2 to 3. So it is given over here, this is the energy level 1, 2, and this is the energy level 3. So electrons are here, so one electron is jumped from energy level 2 to energy level 3. So this is the transition. So what would be the energy difference between these two levels? This is we are going to calculate by using this molecule. And here another important part is the what would be the length of this box. So this is another pictorial picture. It is given over here, the energy level 1 and the energy level 2. And these are the highest occupied molecular orbital. And this is the least unoccupied molecular orbital, or the lowest unoccupied molecular orbital. So electron is moving from energy level 2 to lowest unoccupied molecular orbital, and this we have already studied. This is the wave function of the energy level 1. This is the half. For the second it would be the complete 2 half. For the third there would be the 3 half, and these are the molecular orbitals which are displayed over here, how they are moving. The electrons are moving in the molecular orbital. So here the same equation you can use to calculate the energy difference. Again, this is the energy of any level, and this is the difference in energy level, as we have used this equation in the previous calculation. And again, in the previous lecture it is recorded over here. You can again watch how to derive this equation. Now I am using another way to calculate the energy difference. You can also 100% You can also use this equation, the difference in energy level, but I am going to show you the more easiest way to calculate the difference in energy level. So here the n is the small n is the energy of the nth level, any of the nth level, and capital N is here the number of the carbon atoms. So if you are confused with the or you are unable to calculate the nth energy level, what would be the transition from one energy level to the another energy level? So you just calculate the number of carbon atoms, and these must be the alternate single and the double bond. So this is the easiest way to put the value of the n. So here again, this number n over 2 is equal to the quantum number of the highest occupied level, which we have already discussed in the previous slide. This is the highest occupied molecular level, and this is the number 2. And the transition will be going from this level to the, of course, n plus 1. So of course n plus 1, that mean 1 plus the lowest uh, molecular orbital from where the transition is going to happen. In this case it is from 2 to 3, and that's why it is written over here. It must be plus 1, and this I have discussed detail in this equation as well. So you can also use n by 2 and n by 2 plus 1 in this equation. So this is the difference in energy level as we have derived this equation. And when you put the value again, this is the n plus 2 plus 1. You can take a common of this one, and then you have to open as we have done before by using this very simple formula. A plus b square will be equal to a square plus b square plus 2ab. So this would be the a and this would be the b. When you solve, you would get the value of this one. So the difference between these two equations, this is the energy of the nth level, this is the n is the number of the carbon atoms. Again, as we have done before, you can either put the value of delta E over here, and first you get the value of the frequency, and then you put the frequency over here and get the value of the wavelength or the absorption spectra or the absorption wavelength of any of the molecule. So there is another way. I am just putting the value of delta E over here, and and then you collectively calculate the wavelength by using this equation. So this is the already just the rearrangement of this. First you have to put the value of over here, and then this whole mu you put the value over here, and you will get the value of the lambda. So I am putting the values of the this butadienes, and there are how many carbon atoms? There are the 4 carbon atoms are there. And now the important part is the what would be the length of the box. So that's why I see this calculation is more appropriate as compared to the previous one, because here you have to calculate individually what would be the length of the carbon-carbon single bond and the double bonds. And here let's start with the bond length. 1.54 angstrom or the 154 picometer for the carbon-carbon single bond, and 1.35 angstrom or 135 picometer for the carbon-carbon double bonds, plus the distance equal to the carbon atom radius at each end of the carbon, and this is the 77 picometer. So now I'm going to calculate the length of the molecule, and 135 multiplied by 2. 135 is the length of the carbon-carbon double bond. So there are 2 carbon-carbon double bond. That's why I have multiplied by 2, plus 154 picometer. This is the length of the carbon-carbon single bond. There is only one single bond is there, and there are the 2 terminal atoms. with the radius of 77 picometer. That's why you have to multiply by 2. When you solve this one, you will get the value of 578 picometer or 5.78 exponent minus 10 meter. So you have done with the basic information. That means this is the length of the molecule or the length of the box. These are the total number of carbon atoms. Now you have to put the values over here. You may either use this equation or you can also use this equation. You will get the same answer. So I'm going to explain you over here. So lambda would be equal to, this is the 8, m is the mass of the electron, length is, L is the length of the molecule of the box, C is the velocity of the light, H is the Planck constant, n plus 1, there are the 4 number of carbon atoms are there. So 4 carbon atoms plus 1, so you will, the answer would be the 8. And this is also will give you the same 5 as there are, because the energy level, there is the transition of the electron from the uh, second energy level to the third energy level. So the value of n is 2, as I have shown over here. There is the n, the value of n is 2 because the transition is going on from energy level 2 to 3. So here, if you put the value of n is 2, so 2 multiplied by 2 is 4 plus 1, that means 5. So this is also giving you the 5 and this is also giving you the 5. So there is no difference between this equation and this equation, only the explanation or the information you are putting over here is different, and the difference is I have already explained. So when you solve this one, you would get the value of 2.20 exponent minus 7 meter, or it would be 220 nanometer. And this, you must be surprising to know that know the experimental value of this molecule is 217, and this is the calculated value. And you may see this is the remarkable good and agreement with the quantum mechanical approach to calculate the absorption wavelength and with the experimental value. So in this way, you can calculate the wavelength of any of the polyenes molecule, and this is the very, very important application of the quantum mechanics. And this is the translation movement of the particle in one-dimensional box. So this is all about our today lecture, and I have done the calculation with this 1,3 butadiene, and there are the two examples are given over here, 135 hexatriene and 1357 octatriene, and this you have to calculate in by yourself, and you will share your slides in the coming lecture. So we will be discussing again. So this is your assignment. You have to do yourself, and we will discuss in the future lecture.